Welcome to another exciting educational video brought to you by Upvision Concepts Academy. So in today's video, we'll be looking at electrolysis, and we'll see an introduction into electrolysis. So what it means, electrolysis of aqueous solution. We'll look at Faraday's laws of electrolysis. Who is Faraday? First and second law. He has two laws. And we'll look at some past questions and then answers. So sit tight as we start this topic. Make sure you subscribe if you're not subscribed to our channel to get more of our content. So what is electrolysis? So electrolysis is a chemical process in which electrical energy is used to drive a non-spontaneous chemical reaction. Okay, typically involves the decomposition of an ionic compound in molten or aqueous solution using a direct current. So it occurs when we have an electrolytic cell. So this is how it looks like. You have a cell. This is a container. This is also a container that we have an aqueous solution like this. That solution could be any solution like a chemical compound, and we'll insert two rods known as electrode. It could be two metals or two kinds of metals. The positive side and negative side, two elements. One is the anode, and the second one, negative, is the cathode. That's what it's called. And it is passed through terminal wires that we'll go and link. It's a complete circuit. Let me just go into this way. So there's a battery, electromotive force. So once this circuit is completed, current begins to flow like this and flow through here. So this current can also flow into this solution and liberate the solutions. So if you have a solution here, and let's say I have a copper sulfate solution inside here. So inside copper sulfate solution, the ionic form is copper positive and sulfur dioxide, sulfur radical. So this one that is positive will migrate to the cathode, to the negative charged terminal. And so that is negative, we migrate to the anode. So the copper is deposited at the cathode, and this sulfur is deposited at the anode. Okay, this is just a simple description of what it is all about, but we'll go in more and discover. So, like I said, electrolysis occurs in an electrolytic cell. So this is called electrolytic cell. The whole of this can be spelled on the board. Electrolytic cell. So it's a cell. Okay, and it consists of two electrodes. These are called electrodes. So one electrode is called the anode, positive charge, and the negative one is called the cathode, negative. Sorry, the anode is positive charge, and the negative one is the cathode. Okay, so a direct current source, this is a direct current source from our cell or battery, is applied on this setup, and you see that it brings about the decomposition of the solution. This solution can be anything, can be any solution that can conduct electricity. So by the time you put it now, you can now separate the solutions into the positive and negative side of it. So we're going to be looking at electrolytes and non-electrolytes. So we have on the board electrolytes and non-electrolytes. So electrolytes are actually substances that conduct electricity, these ones. And non-electrolytes does not conduct electricity. Okay, so this one are actually a molten or aqueous form. So when it conducts electricity, what it does is it produces free ions. That diagram I drew, free ions, so that they can move either to the cathode or the anode, depending on the polarity. Okay, so examples of electrolytes, that is examples of substances that can conduct electricity in molten form Number one, I have sodium chloride. Sodium chloride. Sodium chloride. So this is the formula, sodium and chlorine. Then number two, I have sulfuric acid or sulfuric acid. H2SO4. Then number three, I have potassium hydroxide. Potassium hydroxide, KOH. Number four, we have copper 2 sulfite. Copper or cuprum. Copper 2 sulfates. Okay, so this is copper 2 sulfates. I use this one as an example in the previous. So non-electrolytes are actually things like distilled water, sugar. Okay, let me put examples of non-electrolytes. Examples of non-electrolytes. So number one, you have distilled water. Distilled water is that very pure water used in the lab without any contaminants. Sugar solution. Sugar solution, this formula for sugar solution, C6H12O6. Okay. Ethanol is another non-electrolytes. Ethanol, these ones, if you pass electricity to them, they will just be looking at you. They will not do anything. So this is ethanol. Okay. Okay, so we'll go into electrolysis of molten salt and aqueous solution. Okay, so we'll look at an example. Okay, so we'll look at electrolysis of molten salts. Molten salts. Okay, so we're going to take example sodium chloride. So if I have, let's say if I have this, let me just put it here. This is the cell. Remember, this is the cell. Okay, so this is anode, positive, cathode, negative. Then inside here, I have salt, sodium chloride. Let me do it like this. So inside here, I have salt, sodium chloride, right? Now, when we pass electricity through this, understand? This is the anode. So at the anode, you see that inside here, once electricity is passed like this, it breaks what this solution, sodium chloride solution, into its components, sodium and chlorine ion. You understand? So at the anode, what happens at the anode? At the anode, this chloride ion migrates towards the anode. Why? Because anode is positive. So and this one is negative. So it's like a kind of attraction. So this one migrates towards the anode and loses electron, to become because it has so much electron. So it loses so much electron to become the chloride or chlorine. So it is deposited at this point as the non-metal, which is the chlorine. Now the formula at the anode is like this. Anode is positive, right? So this ion, two of it, negative ion, will have to lose electron to become this guy. You understand? And the process of losing electron is oxidation. So look at this term. Oxidation occurs at the anode for this electrolysis. It occurs at the anode. Why? Because the ion that has been molten, that has been liberated, because once electricity is passed, this sodium chloride is split into two, split into the constituents. You understand? So the negative one goes to the positive anode, and the positive one goes to the negative cathode. So for the negative one to go to the positive cathode anode, it has to acquire electron because it is coming as an ion that has lost electron. You understand? So that has gained electron, sorry. For it to be negative, that has gained electron. So for it to become neutral, to be deposited here as just the chlorine, it has to gain electron. So that gain is oxidation. Remember, I defined it under redox video. Remember, the mnemonic is oil rig. Oil rig. So this oil here is oxidation loses. Oxidation is loss of electron. OIL. Oil. Oxidation. So this guy now loses electron. You understand? So oxidation is loss, and reduction is gain of electron. Now, on the cathode side, this is the cathode side. What happens? The chlorine, the sodium ion goes and acquires an electron, because at this point it has already lost electron. That's why it's positive. So it has to want to acquire electron and goes to the cathode. So the process of it adding electron, it now becomes just sodium neutral, and this process is called reduction. Why? Because electron is gained. See, gain in electron. Electron is gained in electron. Electron is gained. Sodium ion gain electron to become sodium, and this sodium is deposited at the cathode. This cathode, this anode. So I've explained it, the way as simple as it can be. Let us look for another solution. If this solution here becomes sodium copper sulfate, copper 2 sulfite. So if this solution becomes copper 2 sulfide, let me write it here, draw it here. This is the anode again, and the cathodes, and the solution here is copper sulfide, right? Okay, so anode is positive, right? Cathode is negative. All right, so if I have it like this, once electricity is passed like this one is broken into the two ions. So I have copper ion and the sulfate like this. This sulfate, the radical, will migrate towards the anode, right? Okay, so at the anode, what happens? We said again, the anode is where oxidation takes place. So at the anode, okay. So at the anode, you have what we call the oxidation of water. So it is water that actually migrates towards the anode, and oxidation of water occurs. So it goes to lose electrons. These are the electrons that you lost, and actually oxygen is deposited, at the anode. But interestingly, what happens at the cathode is that copper goes to acquire electrons. So copper ions add electrons to become copper. So this copper is deposited here at the cathodes. Copper is deposited here. Then here I have oxygen instead. Oxygen is liberated at the anode. So oxygen gas is evolved at the anode. So when active electrodes like copper is used, the copper anode dissolves and copper ions and replaces copper ions in the solution. So also it depends on the electrode that is used. So when active electrodes like copper are used, understand, copper ions dissolves and replaces copper ions in the solution. Okay, so we'll dive into Faraday's law of electrolysis. There are two. Faraday is actually the guy that studied electrolysis in depth and came up with laws that will help us to understand electrolysis and also to apply the quantitative aspects, like the calculation aspects, electrolysis. So Faraday's law of electrolysis, the first law states that the mass of substance M deposited on the electrodes during electrolysis is directly proportional to the quantity of electricity that is passed through the electrolyte. Okay, and this is where M is the mass, where M is equals to mass of substance deposited at the electrode. So, you know, electrolysis will not be complete until there's a deposition of substance on the electrode. That substance deposited is coming from the aqueous solution that's used for as electrolyte. Okay, and Q is defined as the quantity of electricity. And by formula, that Q is equal to IT. I again is current and T is time in seconds. Current in amperes and T in seconds. So when I put this into this equation, I have M is proportional to IT, and when I remove this population constant, I'll be having something like M is equals to KIT, and K is the constant of proportionality. So we'll look at K later. Okay, so 1 farad is equivalent to 901 farads. 1 farad is equivalent to 96500 coulombs. Okay, this is just the first law. But second law states that when the same quantity of electricity is passed through different electrolytes, the mass of substance liberated is proportional to their equivalent weights. So for the second law, M is proportional to the weights, equivalent weights. Okay, so these are the laws of electrolysis, first and second law. We are going to be applying it. You will see some examples in the description. Just note how these formulas are and how it's applied. Further lessons can be contracted if I'm contracted to do it for you for more explanation. But this is actually the breakdown of electrolysis, the two laws, first and second laws. Okay, so what are the uses? What are the applications? How do I apply electrolysis? So the first application is electroplating. Okay, so I will just take this off. Okay, so we'll go to the applications of electrolysis. Number one application is that it is used for electroplating. That is silver plating and spoons. So electroplating is just like electrical coating to give to the metal, to give it aesthetic, make it more beautiful. You use another metal like silver or gold to make it beautiful, understand? And also for protection. So second application is extraction of metals. So we looked at the previous video where we saw aluminium being extracted from bauxite, and that process is through electrolysis. So this is how we can apply it. Thirdly, you can also electro-refine metals. Okay, refining just make copper more polished. Understand? That is electro-refining. Then fourthly, under applications of electrolysis, we can manufacture chemicals like chlorine, hydrogen, sodium hydroxide, and so on via electrolysis. And lastly here, we have the electrolysis of water to produce hydrogen and oxygen. So hydrogen which can be produced in the lab using water electrolysis to achieve that. Okay, so I have on the board a practical question that we'll look at. It says a current of 2.5 amperes was passed through a solution of copper 2 sulfate, this is the chemical compound, using copper electrodes for 1 hour. So calculate the mass of copper deposited on the electrode. So we said that the number of moles is directly proportional to the quantity of electricity. Number of moles or mass proportional to the quantity of electricity. And if this is removed, number of moles will now be equals to kq, where k is the constant known as the farad, the inverse of the farad. So k is 1 over the inverse of, 1 over this Faraday's constant. Let me just put F there. Okay, this Faraday's constant depends on the number of electrons that was emitted or broken down. So for this one, if I write the ionic formula, I have Cu will give us, I will have 2 of it. It will add electrons at the electrode, add electrons, 2 electrons to become copper deposited. Okay, so because it is 2, my Farad constant will now be 2. One of it will give me 96,500. So 2 of it will now give me 193,000. Okay, so what we will do is to first of all plug in the electrical constants, the electrical values. Okay, we know that this one is the quantity of electricity. I'm trying to explain it briefly. Okay, so I have Q will now be IT, and what is I? Current is 2.5, and time is 1 hour. I think I saw 1 hour here. Yes, 1 hour. So, and 1 hour is 1 times 60 times 60. Why? I'm converting the hours into seconds. So, quantity of electricity, which is IT, which is this one, will give me 9,000 coulomb. 9,000 coulomb. By the time I do the math here, so I've gotten this one. And number of moles is mass in gram over relative molar mass. The mass in gram is what we're looking for, calculating the mass of copper. But relative molar mass is given as this. So, and you know that since we have 2 molecules of copper there, my molar mass will now be 6.5. Sorry. Yes. So I will have this component here. This component here, this one is here, and the constant is 1 over F. So let me just put everything in this formula. This is what I'm looking at, this formula. Okay, so number of moles is this one, right? So I'll just say, from here, I'll just say MIG over RMM is equals to, the K is 1 over. So because 1 farad is 9,600, 2 farads, because it's 2 electrons added. Understand? 2 electrons is added. 2 farad will now become 2 times 96500. So this for this component. And for Q, I have it as 9,000. Okay, so RMM is already given as 63.5. RMM is given as 63.5. So what I will just do is to make M such a formula, that's mass in gram. So mass in gram is equals to RMM is 63.5 times 1, understand, times 9,000, then times 193,000. Because this time this will be this. Okay, so by the time I compute, I'll be getting the mass in gram. This one, mass in gram will now be, by the time I compute this one, I will get 2.96 gram. So 2.96 gram is the amount of copper that will be deposited. So you will see some of all these questions in the description and in the comment section. But I would also want you to subscribe to our channel, and then also send us an email or a call or WhatsApp message to book for further lessons. So I hope this video has been informative for you, and I'd like to thank you for viewing.